Nowadays, when you use your internet browser, for example, or you use internet banking or other applications that are encrypted, then the common encryption paradigm that is used for these kinds of protocols is public-private key encryption. And you have likely already heard about this. The basic idea is as follows. First of all, I'd like to introduce two characters that are very familiar in communication problems and information theory and cryptology, Alice and Bob. And I found here Alice in Wonderland and Bob the Builder. They are our two characters, Alice and Bob, and they would like to communicate with each other. Alice would like to send a message to Bob, and there might be an evil eavesdropper along the way in the middle who opens the message and reads the message. And that's, of course, what the two would like to avoid, and therefore they resort to cryptography. Now, the basic idea behind public-private key encryption is that Bob, so the receiver of the message, posts publicly a public key. So this public key is visible to everybody, and Bob tells everyone who would like to send him a message to please use his public key to encrypt that message. So Alice uses Bob's public key in order to encrypt the message, and then this makes life very hard and unpleasant for the eavesdropper. Now, in principle, if you know the public key with which you encrypt the message, then in principle you are able to invert this encryption. So in principle, given enough computational resources, the public key or knowledge of the public key can be used to undo the encryption. However, the commonly used cryptographic protocols, they exploit the fact that certain mathematical problems are computationally very hard. And one of these mathematical problems that are computationally very hard is the factorization of large integers into their prime factors. So if you have a very large integer, which is the product of two prime numbers, then, and you know that, then finding these prime factors is computationally very hard. There's no known algorithm which solves that problem, which does the factorization efficiently. Yeah, so with all known factorization algorithms, the computational resources, the computation time that you need grows exponentially with the length of the number that you want to factorize. So the modern encryption algorithms are designed in such a way that undoing the encryption with the public key amounts to solving the factorization problem, which requires exponentially growing computational resources. And if only you make the key long enough, then with present-day computers, you would need a computation time which, I don't know, if you can make as large as you like. You can make that computational time longer than the age of the universe. So the security of these encryption protocols is based on the fact that this mathematical problem is hard. Bob, of course, when he generated his public key, he simultaneously generated a corresponding key which helps him do the inversion and decrypting the messages that he receives. So Bob has simultaneously with his public key has created a private key, which is the counterpart of his public key, which allows him to quickly decrypt any message that he receives. And of course, this private key he has to keep in a very safe place, because anyone who gets a hold on this private key will be able to decrypt the messages. One of the reasons why people are interested in quantum computation, one of the many reasons, is that there exists, at least on paper, an algorithm, that's the so-called Shor's algorithm, which does the factorization of integers efficiently. So if a quantum computer could ever be built that's large enough to do to implement Shor's algorithm, then today's common encryption algorithms would no longer be safe. The quantum hardware is not there yet, and most people say that's still pretty far off. But the theoretical possibility exists. And of course, you never know how fast technology progresses. So potentially, many of today's encryption algorithms could become unsafe one day. And this is one reason why there's renewed interest in another form of cryptography, which is private key encryption. So there's no longer a public key, but Alice and Bob share a private key. And then Alice encrypts her messages with that shared private key, and Bob decrypts it with the same, or with sort of the corresponding decryption key. Now, this kind of encryption can be proven to be secure if Alice and Bob don't use the same private key too often. So if they regularly change their shared private key, then an eavesdropper will not be able to accumulate enough data from past correspondences between the two that would allow the eavesdropper to learn the private encryption key. Yeah, so if Alice and Bob use private keys and they change them regularly, ideally they use sort of one-time private keys, and then for the next communication they use another private key. So an eavesdropper never has a chance to learn anything about the communication or discover any patterns in the communication between Alice and Bob. And this can be mathematically proven to be secure. This kind of encryption, however, poses a practical problem, because this is only secure, of course, if Alice and Bob initially have a way of sharing this key in a secure manner. So they might meet in a secure room, and then Alice hands to Bob a sheet with the private key, for example. But this would mean that every time that they want to communicate, they would have to physically meet in one place and exchange a private key. And this is, of course, for practical purposes, extremely inconvenient. So whenever you want to use private key encryption, the main practical challenge is to devise a way for Alice and Bob to share a private key without having to meet physically in the same place.